A-Level Pure 1 Sequences, Geometric Progressions. Let's see what we mean by a geometric progression. Consider the sequences 1, 2, 4, 8, 16, 32, and so on. 7, 21, 63, 189, 567, 1701. 250, 50, 10, 2, 0.4, 0.08, and so on. In each case, it's easy to spot a pattern. In the first example, we start with 1 and keep multiplying by 2. In the second example, we start with a 7 and keep multiplying by 3. In the third example, we start with 250 and keep multiplying by 0.2, or dividing by 5. If we start with one number and then keep multiplying each term by a constant number to get the next term, we call the sequence a geometric progression or a GP. Now let's introduce some notation. We use the following notation for a GP. We use the letter A for the first term, R for the common ratio. This is the number we multiply a term by to get the next term, and Tn as the nth term. So a GP would look like A, AR, AR squared, AR cubed, AR to the power 4, and so on. From this we can see that the nth term, Tn, is equal to A times R to the power n minus 1. Now we have the n plus 1th term is equal to R times the nth term. So R is the ratio, the n plus 1th term over the nth term, Tn plus 1 over Tn. So R is the ratio between consecutive terms. Let's have a look at an example. The third term of a GP is 120, and the 8th term is 122,880. Find the first term and the common ratio. Well, to solve this, we've got T3 is 120 and T8 is 122,880. So AR squared is 120 and AR to the 7 is 122,880. So AR to the 7 divided by AR squared is 122,880 over 120. And that cancels down to R to the power 5 is equal to 1024. So R is the 5th root of 1024, which is equal to 4. Now we know AR squared is equal to 120, so A times 4 squared is 120, which means 16A is 120, or A is 7.5. So we have the first term is 7.5 and the common ratio is 4. So we have an important result. The nth term, Tn, is equal to A times R to the power n minus 1. Let's look at a second example. The nth term of a GP is 15 times 4 over 3 to the power n. Find the first term and the common ratio. Well, to solve this, for the first term, n is equal to 1. So T1 is equal to 15 times 4 over 3, which is 20. Now for the second term, n equals 2. T2 is equal to 15 times 4 over 3 squared. So it's equal to 15 times 16 over 9, which cancels down to 80 over 3. Now the common ratio is T2 divided by T1. So it's 80 over 3 divided by 20, which is 4 over 3. So the first term is 20 and the common ratio is 4 over 3. In example 3, we've got the sum of the first 3 terms of a GP is 91. The first term is 7, and we have to find the common ratio and the first three terms. Well, to solve this, if the first term is 7, then the second term will be 7r, and the third term will be 7r squared. Now the sum of the first three terms is 91, so 7 plus 7r plus 7r squared is equal to 91. And if we divide all the way through by 7, we get 1 plus r squared is equal to 13. And that can be rearranged as r squared plus r minus 12 equals 0. And that factorises as r plus 4 into r minus 3 equals 0, which means r is equal to minus 4 or r is equal to 3. So the common ratio is 3 or minus 4. Now if r is equal to 3, the first three terms are 7, 7 times 3 and 7 times 3 squared. That is 7, 21 and 63. If r is equal to minus 4, the first three terms are 7, minus 28 and 112. Now let's look at the sum of the terms of a geometric progression. If we add the terms of a GP, we call it a series. Let's consider the series 5 plus 15 plus 45 plus 135 plus 405 up to 71,744,535. This is 5 plus 5 times 3 plus 5 times 3 squared plus 5 times 3 cubed plus 5 times 3 to the power 4 and so on up to 5 times 3 to the power 15. This has 16 terms. Now we could work this out by the following method. Let S equal 5 plus 5 times 3 plus 5 times 3 squared and so on up to 5 times 3 to the power 15. Then multiplying by 3 and then subtracting the original gives 3s is equal to 5 times 3 plus 5 times 3 squared plus 5 times 3 cubed and so on up to 5 times 3 to the 15 plus 5 times 3 to the 16. And underneath we can write s, which equals 5 times 5 times 3 plus 5 times 3 squared all the way up to 5 times 3 to the 15. Now if we subtract, we have 2s, and a whole lot of the terms on the right-hand side cancel out. And on the right-hand side we're left with minus 5 plus 5 times 3 to the 16. So 2s is equal to 5 times 3 to the 16 minus 5. Or s is equal to 5 into 3 to the 16 minus 1 all over 2, which actually works out to be 107,616,800. Now this is a much quicker way of working it out than, say, going through all the terms with a calculator. Now we can do this to get a general formula. Suppose we wish to add the first n terms of a geometric series. Sn is equal to a plus ar squared plus ar cubed plus ar to the power 4 up to a times r to the power n minus 1. Now we can multiply by r all the way through and then subtract the original. And this gives us r times s to the n is equal to a times r plus ar squared plus ar cubed up to a times r to the power n minus 1 plus a times r to the n. And underneath we can write Sn is equal to a plus ar squared plus ar cubed up to a times r to the n minus 1. Now if we subtract on the left hand side we have r minus 1 s to the n, and on the right hand side we have minus a, and then all the middle terms cancel out to just leave at the end plus a r to the n. So r minus 1 s to the n is equal to a times r to the n minus a. Or we can rearrange that as s to the n equals a into r to the n minus 1 over r minus 1. Now another way of writing exactly the same thing is Sn is equal to a into 1 minus r to the n over 1 minus r. And these form an important result. The sum of the first n terms in a geometric series, Sn, is equal to a into r to the n minus 1 over r minus 1, or Sn is equal to a into 1 minus r to the n over 1 minus r. Both formulae are the same, but the first is more useful if r is greater than 1, and the second is more useful if r is less than 1. It's worth noting that the formula doesn't mean anything if r equals 1, because you'll have 0 on the top and 0 on the bottom. However, if r equals 1, then all the terms in the series are equal, and so the sum of the n terms will simply be n times a, the number of terms times the first term. So now we have 3 important results, and we can use them to solve problems. Let's look at an example. Example 1. Find the sum of the first 14 terms of the geometric series 5 plus 15 plus 45 plus 135 plus 405 and so on. Well, to solve this, we've got a is equal to 5 and ar is equal to 15. So 5r is equal to 15, which means r is equal to 3. Now, using Sn is equal to a into r to the n minus 1 over r minus 1, we have S14 is equal to 5 times 3 to the 14 minus 1 over 3 minus 1, and we can work that out on a calculator as 11,957,420. And that is our answer for the sum of the first 14 terms. In a second example, we're given the second term of a geometric progression is 375, and the fifth term is 81. Find the common ratio and the first term. Well, to solve this, we've got T5 is equal to AR to the power 4, which is 81. T2 is AR, which equals 375. So if we divide AR to the power 4 over AR is 81 over 375, and that cancels to R cubed is 27 over 125, and if we take the cube root of that, we get R is equal to 3 over 5. Now, we're told that AR is equal to 375, so 3 over 5R is equal to 375, so R is 5 times 375 over 3, which is 625. So the common ratio is 3 over 5, and the first term is 625. Now again, we can use the 3 results. In example 3, we're given the fifth term of a geometric progression is 8 times the second term, and the sum of the first 6 terms is c times the sum of the first 3 terms. Find the value of c. Well, to solve this, we've got T5 is equal to 8 times T2. So AR to the power 4 is equal to 8 times AR. Now the A's and an R cancel, so we're left with R cubed is equal to 8, so R is equal to 2. Now we're also told that the sum of the first 6 terms is c times the sum of the first 3, so A into R to the 6 minus 1 over R minus 1 is equal to c times A into R cubed minus 1 over R minus 1. Now the A's cancel and the R minus 1's cancel, and so we're left with 2 to the 6 minus 1 equals c times 2 to the 3 minus 1. So 63 is equal to 7c, which means c is equal to 9. And that's our answer. C equals 9. In example 4, we're told the first term of an arithmetic progression is 3. The first, 4th and 13th term of the AP form the first 3 terms of a GP. Find the common difference D in the arithmetic progression given that d is not equal to 0. Well, to solve this, for the AP we've got the first term t1 is equal to 3, the fourth term t4 is equal to 3 plus 3d, and the 13th term t13 is equal to 3 plus 12d. So for the GP, we've got the first term, we'll call it u1, is equal to 3. The second term of the GP is the fourth term of the AP, u2 is equal to t4, so it's equal to 3 plus 3d. And u3 is equal to t13, so u3 is equal to 3 plus 12d. So for the GP, the first term a is 3, the second term ar is equal to 3 plus 3d, and the third term ar squared is equal to 3 plus 12d. Now if we substitute a equals 3 in ar equals 3 plus 3d, we get 3r equals 3 plus 3d. And if we divide all the way through by 3, we get r equals 1 plus d. Call that equation 1. Now if we substitute a equals 3 in ar squared equals 3 plus 12d, we get 3r squared equals 3 plus 12d, which means if we divide by 3, r squared equals 1 plus 4d. Call that equation 2. Now in equation 1 we've got r is equal to 1 plus d. So we can substitute in 2 r squared as 1 plus d squared equals 1 plus 4d. Now if we expand the bracket we get 1 plus 2d plus d squared equals 1 plus 4d, and if we rearrange it we get d squared minus 2d equals 0. Now we can factorise that as d into d minus 2 equals 0, which tells us that d is 0 or d is equal to 2. Now we've been told d is not equal to 0, so our answer is d equals 2. Now it's easy to check this. If the first sequence, which is actually the odd numbers starting at 3, are 3, 5, 7, 9, 11, 13, 15 and so on, then the first term is 3, the fourth term is 9, and the 13th term is 27. Now 3, 9 and 27 are a geometric progression with first term 3 and common ratio 3.